Wow, look at my massive army.
Oh my god, look at this tiny feet.
So guys, today I'll be showing you how to do this. So we are updating our navigation system from the previous video and look at them go. So there is a lot to talk about and show to you guys on this video, and I'm going to be trying to explain everything I can the easiest way. So let's see how you're going to be able to do this with your own games. So here we are back in our project that was left on the last video, with our current navigation being like this. And so let's go ahead and fix some of the issues, like the rotation bug. So let's go ahead and fix that. Let's go ahead and create a new rotation function for our units. So let's go to our test unit script. And let's create a new variable that is going to control the type of rotation we are going to get, because we are going to be generating two types. So let's go ahead and create a new variable. So let's use rotation fast variable as a boolean to control the rotation mode. Another thing you're going to need is a new rotation function. So this is the rotation function, rotate to direction. It gets a direction input as a vector 3 and the delta. We check the rotation fast boolean, and this is the code for the snapped rotation, which we have already. This is the same rotation type, but we are now rotating towards a direction and not towards the velocity anymore. The smooth rotation mode works by getting the 2D position and the 2D goal as a vector 2, because the angle 2 using the vector 2 function works differently from the angle 2 using vector 3. And this is how it works. Now, for us to use this, what we are going to do is to change the code here. We are applying the rotation on the character move. We don't want this here. So let's remove this and let's rotate on the physics process right after we get our direction. So right after we get the direction to the next path position, we are going to apply the rotation. And here we can pass the direction and our delta. So now we are rotating using the fast mode. So if we run our scene, it's just like the previous video. And another thing we have to adjust here. Our units are backwards. So let's go back to our unit scene. So if you get to our test unit here, we can see that they are inverted. So in Godot, -z is facing forwards, and as you can see here, it's facing +z, which is not how Godot operates. So if you go to the transform here, you can see the native z is towards that direction, not this one. So we're going to rotate our unit here by 180 on the y-axis and move our selected graphic just here. So now our units should be facing the right position, the right orientation, I should say. And as you can see, it works. And with the new rotation mode being applied on the physics function, not on the move function, we are applying the rotation towards a direction, not towards the velocity. So it fixes that bug we had earlier with the units rotating around. So you can also test the other rotation mode here. If we go to our test unit script and change our rotation mode to false, this is going to get called on our check here, and we're going to use the smooth rotation code, which is this code here. And it uses delta to smooth the operation. So as you can see, they rotate using now delta, which is smoother than the previous function, which snaps the rotation towards something. And you can change the speed of that rotation through the steering speed, which is also used on the physics process to create the steer velocity for our steering behavior. So the steer speed is used for rotations and to rotate the steering here. So if we put something slower, like 1, you can see they will be rotating very slow and also steering very slow. So this is quite nice for us to do big shifts, stuff like this. So you can select the rotation mode by giving here. So this now takes care of the rotation for our units. So let's go back, and I'm going to add here some terrain for us to work with. So I'm going to be dropping on our navigation region here a terrain mesh that I made in Blender. So with this, we should be able to test our navigation a little better. So let's bake the new navigation map, and you can see there's some stuff we need to optimize here. So let's go to our navigation, generate mesh, and let's find where we see about agents. So the maximum slope I'm going to reduce to 30 degrees. This fixes some issues. To remove this type of islands, you can go on the region size and put something here, like 10 on the minimum size. And this will actually delete empty regions that don't have that minimum size. So that fixes some of the issues we have. Another issue we can change here is on maximum climb. We can put something like 0.2, and you also need to update the cell height here as well. So I can actually lower this a bit. So you can see here we have a floating island. So just increase the minimum range and you should get rid of that. Just be careful, because if you put too much here, you're going to avoid the navigation from baking altogether. So let's put here a value that works, like 20. So now if we run our scene, we should be able to make our units move through the map here. And as you can see, it works all right. So let's add more units here for us to be able to test a little more. And holding Ctrl, let's snap their position a little bit so we can duplicate it. So let's grab the 4 units. Let's duplicate this by 1, 2, 3. This will give us 16 units, and this will allow us to keep testing for more units this time. So let's see how this is working. And the idea is for us to find some issues to be able to fix. And one of the issues we are going to be fixing is gravity, because as you can see, our units are not exactly on the floor. So one of the ways we can improve the navigation is by making our units actually float. So let's go to our test unit, and I'm going to be changing the collision shape here to be a sphere, because spheres are faster to calculate. Let's reduce the radius here to 3, and I'm going to be making them float about 0.4. I think that's okay. So the way we are going to be doing is to teleport our units to the ground using a raycast, but the graphics of the units are going to be faked to be on the ground. So I'm going to show you what I mean by that. So let's create a new raycast here, a physics 3D raycast. This is going to be pointing on the floor, and we're going to be teleporting our units back on the floor, because sometimes the unit can float due to the navigation. So now that our units have raycast applied, let's go to our test unit code and let's add a raycast here. So now that we have our gravity raycast on the physics, we are going to say if we are navigating, so we are going to cast our navigation, and let's get a collision point for our raycast. So our unit position, so our position.y is going to be equal our gravity raycast, the collision point dot y position, plus a height difference we wanted. If you just leave at this, the units are going to be stuck on the floor, and you can see how that is going to work right here. So the units are really close to the ground, and as you can see, this is going to be happening. So let's going to fix this. So we need to set the height for our collision. So I don't want to put the collision box closer to the ground, because this is going to collide with the floors on the ground. So rather than do that, we are going to be adding a height difference here on when we use the gravity. So let's increase our Y position by something like 0.4. So this is going to help our navigation by not making our units actually collide with the floor all the time. And as you can see, they float a lot better on terrain now. But for us to give the illusion that the units are actually on the ground, as you can see, they are floating by a height distance here. So to give the illusion that our units are on the ground, we increase the position by 0.4. let's make our graphic of the unit actually be below the ground. So let me test with 0.4 to see how this is going to look like. And we want to give the illusion that the units are still on the ground, but while the physics body are actually floating somewhat. This is going to help the collision with the world, because we are not going to be using move and slide. So as you can see, they are giving the illusion that they are on the ground, but they are actually floating a little bit, and this helps the physics process a lot. But because we are using move and slide, which is more accurate, you can see they are trying to get on top of another, but by each physics frame they get teleported back to the raycast position to the ground. So we are going to be changing our move and slide function to be used only with static colliders, such as a map. But units when colliding with each other, to improve performance, we're going to change our script to use move and collide instead of just move and slide. So let's change how our units are moving right now. So let's go to our test unit and let's see our character move function. And as you can see, it's using move and slide. So let's change how this is being performed here. And again, the reason that I'm changing this is because move and collide is a lot faster than move and slide. Because move and slide is actually calling internally move and collide various times. And you can actually set the amount of slides you are using with move and slide by doing set maximum slides. And this allows you to set the maximum amount of slides, and I'm going to be reducing to only 2. So if you check this is a function of character body 3D. It's the maximum number of times a body can change direction before it stops when calling move and slide. So this is only for move and slide. And move and slide is more performance costly than just move and collide, which produces a kinematic collision 3D. So the idea is to use move and collide for other characters to improve performance, and use move and slide when we collide with the map world. Because move and slide is more accurate, it's going to help us with colliding with the world. So how do you actually use move and collide? So move and collide returns a kinematic collision 3D, which we are going to use to checking for collisions. And here you can pass the new velocity for our function multiplied by delta. So let's get our physics process delta time, because delta is out of the scope of this function. So now that you are doing this, we can actually go right here and say if collision. So if we actually collided with something, we want to get the collider, so who we collided with, and collider is an object. So collider is from the collision.getCollider. So this is going to return either a character body 3D or a static body 3D. So if our collider is a character body 3D, we want our velocity to slide through that body. That is how you can apply. That's how you can emulate the move and slide. So new velocity dot slide, and we want to slide through the collision dot get normal. So I'm going to disable this for you to see what is happening here. So we are not actually using move and slide anymore. We are only using move and collide. So if we run our scene and move our units here, you can see that once they collide with each node, they stop. And they don't push one another, they just stop. And as you can see, this can get quite problematic on these areas. We want the units to slide along, and you can see they are stuck here. So how do we fix this? Well, you fix by applying a slide to the vector3 new velocity using the collision get normal. And this helps units slide along each other. So as you can see now, the units are much less to get stuck. Then they slide along one another, which is great. But there's an issue when we collide with the world. So when we collide with the map, so let's put another elif here, and I'm going to be saying collider is static body 3D. So when we collide with the world, we actually want our velocity to be changed here. So when we collide with the world, we want a move and slide. And the reason we are separating the movement slide for static body and character body is because movement slide is more expensive to be called. And because I'm using 200 units, I tested and move and collide is much faster. So against other character bodies 3D, we're actually using move and collide. So with this code, it's almost the same behavior. It just performs a little bit differently. So let's run our scene. And as you can see, the behavior is almost the same, but it is different in some aspects. So let's continue here. And let's make more units to see some of the issues we are having. So let's duplicate this by a little more. Let's make more units. So right now we have a bunch of units. We have 64 units. So let's see how this is behaving. And we are going to deal with some of the issues that you have right here. So units are close to the goal, but they do not reach the exact center position. So we are going to actually fix this. So now let's go through an important function, which I'm going to call the stuck function. So let's go to our test unit here, and I'm going to create three new variables here. A stuck max, count, and a last position. So we'll be recording the last position to calculate our distance to the movement goal, which is nav path goal position. And if that distance is short enough, we're going to increase our stuck count until the max. And this is going to be used for us to cancel our navigation if we are close to the path point. So let's go ahead and let's create our stuck check function. So as you can see here, that is how the stuck function works. We check if our last position distance squared to our global position is less than a given minimum value. And you can also multiply this by the movement speed of your unit. So if our stuck count is less than max, we increase the count by 1. Then we check if our stuck count is higher or equal to 3. Then if our global position distance squared to our nav goal position, so this is like the mouse movement goal position, it's updated on the input function. So if the distance to our goal destination is less than 10 or our stuck count is higher than stuck max, we're going to cancel the navigation and we'll reset the stuck count. And cancel navigation can be a function as well. And you're going to call the stuck check not on the physics frame, but rather on the nav path timer updated. And also, it's quite important then after we check for the stuck, we update our last position. So our last position will be equal to our global position. So now that you have this, you should be able to make our units stop if they are close enough to their movement destination or if they got stuck for a long period of time. So if we run our scene now and move our units, you can see they will stop moving after a couple of seconds here. And of course, I forgot to leave here cancel navigation. So if we run our scene now and move our units to something like here, you're going to see that after a while, units will cancel their navigation and stay put where they are. So some units will cancel the navigation because they are close to the target destination. And some units will cancel the navigation because they got stuck trying to move to the destination for too long. And too long is calculated by the amounts of time our stuck gets updated. So now if we move our units to somewhere like here, units in the back here, they got stuck for a while are going to be cancel their navigation. And one of the ways we can improve this behavior, it's by going here on our timer. And let's set the timer to have a little more time. So for now, our timer is about 0.25 seconds. Let's increase this to 0.1 seconds. So now if we run our scene, the stuck count is going to be increased by that whenever that time runs out and we are still close to our last position. So if we run our scene now, you should be able to see a nice behavior of units. So units that get stuck for a while will cancel their navigation if they are close to the path destination or if they got stuck. So units in the back here will cancel their navigation. So as you can see, this behavior somewhat fixes the issue of units trying to always get through a single position. Because without that, they will not cancel the navigation. So units that cancel the navigation around here is because the navigation agent reached the path desired distance. So the navigation agent has this property here, the path desired distance, and this will basically stop units when they reach 1 meter of their goal destination. However, that is not possible when you have a bunch of units around. So this is a solution for us to deal with multiple units. And as you can see, after a couple of seconds, the nav timer is going to run out and the stuck count is going to pass, and we are going to cancel the navigation. And this also improves performance because we are not trying to move to the goal destination. Something we can also do to improve the navigation avoidance is to increase the radius past the collision point. So on the previous tutorial we set the radius to be the same as the collision shape. However, if you increase it a little above, it's going to help the avoidance algorithm. So another thing we can do is to randomize our goal position a little bit. So let's go to our input position here. And when we left click to move our units, let's get our camera raycast coordinates and let's add a randomize vector tree. So we want to randomize on the X and Z position, not on the Y, because we do not want to move our units on the Y axis. So by us adding a randomized vector tree with its X and Z position randomized a little bit, we'll be able to spread apart our units a little more. And this is going to help the navigation and the appearance as well. So when you click somewhere, it's going to randomize all the goal position, and the units now will have different paths to move, and it's going to look a little better than try to move to a single position. So as you can see now, units should move a lot better now, which is pretty good. And by the way, one of the issues you have when using units is the following. So you notice when we move our units, they are trying to get above one another. That's because actually of our raycast. Because our raycast for the units, our gravity raycast is calculating the raycast based on the collision shape of 1. However, our units are also on the collision layer of 1. So if you go to our character body 3D here, you can see they are on the layer 1. So what you want to do is to separate the layers. So let's put our units on layer 4. So now only the raycast is going to be against the map instead of all the units. So let's rename the collision layer here just for us to know what it's all about. So now if we run our scene, you can see that it improved a lot the raycast, and it's not going to try to move above other units. So when you move to somewhere like here, it's not going to step on other units because the raycast is only now consider the map because it's only layer 1. So this is also to improve. So now we can start to increase the number of units to see how this is going to be behaving on our game. So let's grab all the terrains we made and let's duplicate it. So then we bake our navigation mesh, check for any issues. So now let's go through our units, and I'm going to select all the units here, put it on the back. I'm going to duplicate our units. So we have now 128. Let's make a little more and a little more. So I want to have the same amount that I have from my previous test because on my computer this run the best. So about 200 units was the best it got for me, at least on my computer here. So now if we run our scene, let's see how the units are behaving. So we have now 200 units running together. And you can see the FPS will chug along a little, but overall it's workable, I would say. So about 200 units is the maximum for my hardware here. So as you can see, the units navigate now almost the same as my project, and there's no secrets. That is everything that I did. So keep in mind this navigation is not finalized. You can also improve it a little further. So a lot of these behaviors will be able to be controlled through the map level that you are making. So you can see units are sliding outside of the map. So to prevent this, just create a map that has higher walls or some areas where you don't want them to walk, just place some static bodies to prevent this from happening. So a lot of this is also working against issues you're going to have. So this is not like you're providing a solution that works for all cases. You're actually fixing bugs as they appear. So at the moment, I'm quite happy with the navigation system that I have. So this is what your players will be seeing while playing the game. And as you can see, pretty good stuff. And if you wanted, you could disable the stock algorithm that I made to the units not skip. So if you don't want these behavioral units being left behind, you can increase the stack counts. So if we go to our test unit script, so what you can do is increase the stack max like 20. So after 20 times the navigation path timer gets called and finds that the unit got stuck, we are going to be cancel the navigation. So now units will not cancel the navigation whatsoever. It's going to take a lot longer for them to cancel that. So as you can see now, the units don't get left behind at all. So this of course depends on the behavior you want. You have to fine tune a lot of this to the things you want. For me, I think that's alright because I'm actually trying to improve performance. So I'm making some trade-offs here and there. So there we go. As you can see now, the behavior is a little different. So I hope you find this tutorial useful, and put down in the comments if you have any questions. I will help as best as I can. Like the video if you find useful, dislike if you didn't, and I'll see you in the next one.
Look at them go!
Bye everyone, until the next video. See ya!